Good data is essential to making informed decisions in conservation planning. In this video, we will overview some of the techniques and tools that are used to collect data on biodiversity. One of the most basic ways that we collect data about biodiversity is by putting boots on the ground, by putting actual humans in the field and conducting surveys of a particular area. Although this method can be time-consuming and expensive, it can produce critical information and data that cannot always be replicated through a more technology-driven method. This is especially true when looking to survey very small things like insects or small plants, which are hard, if not impossible, to capture with other methods like cameras or drones. Still, technology can be used to make things easier and to streamline the data collection process. For example, GIS has helped us to determine where we need to focus our efforts in the field, and things like handheld GPS units and smartphones have made the collection and eventual processing of data collected in the field easier. While there is value in putting boots on the ground, there is certain data that just can't be collected by people in the field. Camera traps are automatic cameras with motion detection devices such as tripwires, pressure plates, or laser sensors. They allow for scientists to collect data on wildlife without actually having to be in the field, which means that more data can be collected over a longer period of time, and they offer insight into what wildlife do when there are no people around. Camera traps have a surprisingly long history. The first ones were developed in the 1890s by American Congressman George Shiras, who used a tripwire to trigger a camera and flash unit. Now, camera technology at the time was pretty rudimentary, and the flashes were both blindingly bright and extremely loud. So in addition to taking photos, they were also a great tool to scare wildlife. But nevertheless, this new technology produced photos of a sort that nobody had ever seen before, including wildlife at night. These early camera traps weren't really used explicitly for scientific or conservation purposes, but many of the photos they produced found their way into publications like National Geographic. The first known case of using camera traps for research came in the 1920s with Frank Chapman, who was a scientist at the American Museum of Natural History. He was down in Panama doing wildlife census work and was puzzled by a couple of sets of cat tracks that were left outside of the research station he was staying at. He had no idea what type of animal was walking by each night, so he set up a camera trap and was successful, learning that the tracks were made by an ocelot. But this little experiment led Chapman to see the bigger potential for camera traps. At the time, the common practice for determining which species were found in an area was to go on species collection expeditions. Boots-on-the-ground trips where species were surveyed and individuals were killed and taken as record specimens to be further studied in natural history museums. What Chapman realized is that camera traps could be used as a way to survey wildlife without the killing aspect, or as he put it, to census the living rather than getting a record of the dead. Over the course of the 20th century, camera traps were used sparingly in ecological research, as scientists were limited by the high cost, large size, and weight of cameras. However, by the 1990s, camera technology had advanced considerably, and they became more affordable and reliable, which made them more viable as a scientific tool, so they started to become more common in ecological and conservation science research. However, there were still some limitations to the technology. First, the cameras needed to be set out by hand and then collected by people after they had taken photos, so they were limited to places that were reachable on foot. These were also film cameras, meaning that researchers were generally limited to 24 cameras per camera at a time, as that was the standard size of a roll of film. So the cameras had to be checked and the film replaced frequently. But despite these limitations, camera traps became more common and were used to contribute to some very exciting conservation research. For example, camera traps were used to document the Amur leopard in China, which had been thought to be extinct for over 60 years. They were also used to get the first live record of species like the Saharan cheetah and the discovery of new species like the Amurite striped rabbit in Southeast Asia. These were exciting advancements that gave scientists and the broader public a glimpse into the lives of animals when there were no people around. Research involving camera traps got another boost in the early 2000s when digital cameras became more widely available. All of a sudden, camera traps had to be visited less often, as instead of a roll of film for 24 pictures, researchers could leave a memory card that could hold hundreds or even thousands of pictures. Of course, even with all of the advances in camera technology, there will always be some limitations to camera traps. They have to be properly positioned in order to avoid direct sunlight and to not be too obtrusive. Cameras can also only capture the space that they're aimed at, which of course is only a small snapshot of the total area, so there are likely lots of things that even the most advanced cameras are missing. They also tend not to be able to capture small species, so camera trap studies are more useful for large or medium-sized animals. Advances in technology and digital storage over the last decade have also allowed for video to be captured using camera traps, which has allowed for unprecedented insights into animal behavior, especially for some of the most elusive animals and those that are the most sensitive to the presence of humans. The digital era of camera traps and the power of the internet have also allowed for camera traps to become a powerful tool for reaching out to the public, as they allow for people to see places and wildlife that they have never and likely will never see in person. For example, Wildlife Insights has made over 21 million camera trap records from over 10,000 cameras in 65 countries publicly available. This massive amounts of data coming from camera traps has also increased the need for artificial intelligence to help analyze the data, which we will hear more about in a later video. Camera traps are really great for giving us a sense of what species might be occupying a particular place at a particular time, but they don't tell us how different species might be moving around the landscape. For that, we have other tools like tagging, which is when we place some kind of identifiable or trackable marker on an individual animal and then watch its movements. Like camera traps, the tagging and tracking of wildlife has a long history. In 1804, the American naturalist John Audubon was curious as to whether migrating birds returned to the same place each year. So he tied strings to the legs of birds before they flew south, and the following spring he found that indeed they do return to the same places. This was the birth of bird banding. Nearly a century later, in 1902, the Smithsonian started the first formal scientific study using bird bands, which continues to today. In the 1950s, radio technology allowed for significant advancement in tracking studies through the introduction of radio telemetry. The method works through the integration of two key devices. The first is a transmitter, which is attached to an animal somehow, usually as a collar or on a wing, dorsal fin, or carapace. The transmitter then sends out a radio signal, which can then be picked up by the receiving device, like the one you see in the photo here. Initially, researchers had to go out and walk around in the field with the receiving device until they picked up a signal, but advances in technology eventually allowed for receiving devices to be attached to vehicles or planes. In the 1970s, satellites became the main receiving devices for transmitters, which further advanced the technology as it allowed for researchers to get more data over longer continuous periods of time, as they no longer needed to be physically in the field with their receiving devices looking for a signal. Advances in GPS technology in the 1990s further increased the amount and accuracy of data that could be collected about wildlife movement across landscapes. This gave researchers insight into movement patterns on the broad scale, like the paths that birds use to migrate across entire continents, but it also allowed for scientists to learn more about wildlife day-to-day movements, and helped to identify key areas like roosting areas and foraging habitat preferences, as well as determining home ranges. Today, technology in this space is moving fast. Not only are receiving devices getting better and batteries lasting longer, they are also getting smaller and lighter, which makes them less obtrusive on animals, but also allows them to be put on smaller and smaller animals, with some researchers putting tags on bees and others on monarch butterflies to track their movements across North America. We are also starting to be able to track animal movements in 3 dimensions. For example, some scientists have used tracking devices to see how eagles change altitudes at different points in their flight, and others have tracked how Burmese pythons move from the forest floor to up in the canopy. Over the last few years, researchers have been combining the types of data that you get from camera traps with the more movement-oriented data that you get from tagging and tracking by attaching a camera to an animal, usually around their neck or on their head, to get an even finer scale understanding of how different species use their environment. One application of this technology has been to better understand how domestic cats use the urban environment. There's a lot of debate around domestic cats and whether or not they should be allowed to roam freely, as they are thought to be a major predator of songbirds in the city. So Elizabeth Gow from the University of Guelph attached cameras to the collars of cats to better understand what they got up to when they left their owner's home. Her and her team have gotten a cat's eye view of the urban environment, and they have learned about the risks cats face in the urban environment, as well as what and where they hunt, and how they interact with other animals in the city. The final type of data collection that we will look at today is remote sensing. Remote sensing is the collection of data from a distance, usually through aircrafts or satellites. There are a number of different types of data that we can collect through remote sensing, including aerial imagery, infrared imagery, and LiDAR. Remote sensing allows us to monitor and understand large areas easily and quickly, and helps us to observe even the most remote regions of the world. The first images from space were taken on the first suborbital flights in the 1940s, but the first images taken while in orbit outside of the Earth's atmosphere were made on August 14, 1959 by the US Explorer satellite. In 1972, NASA and the US Geological Survey launched the longest-running satellite imagery program, Landsat. Since then, a number of satellites have been launched as part of the program, the most recent of which was Landsat 9, which was launched on September 27, 2021. And overall, the program has captured millions of images of the planet. Because of the longevity of the program, the images are a unique resource for studying global change, and the images have been used in all kinds of research, including agriculture, geology, and conservation. Over its nearly 50-year history, Landsat has kept up with the latest technologies in satellite imagery, and each new satellite that was launched had new sensors, allowing researchers access to even more data. The cameras on Landsat 9 have 8 spectral bands, plus there is an additional thermal infrared sensor with spatial resolutions ranging from 15 to 60 meters, and a temporal resolution of 16 days, so a place on Earth is photographed every 16 days. The launch of the International Space Station in 1998 was another opportunity to capture the imaginations of people through images of the Earth taken from space. Although it is not as automatic and regular as satellite imagery, there is something about a photo taken by a person that just gives us more of a connection. And images taken from the space station have been used to demonstrate change and show the impacts of humans on Earth's landscapes. In 2014, another set of satellites were launched by the European Space Agency. These are the Sentinel satellites, a total of 11 satellites which will be launched through 7 missions through the Copernicus project. All of the data obtained through the project is publicly available for free through the online Copernicus Open Access Hub. Closer to Earth, drones are increasing in popularity, and they are becoming a more common tool for the collection of data in ecology and conservation. We'll hear more about research using drones in our guest lecture this week from Sophie Niedoslavsky.